Welcome back to the deep dive. Today we are tackling probably the single most frustrating problem in high-scale backend development, the slow kill memory leak.
It really is the nightmare scenario for any ops team, isn't it?
It is.
You're running a long-lived application, a big Node.js API, or, and this is a big one, a server-side rendering app like Angular Universal. Everything looks fine. But then over hours, maybe days, your memory usage just starts creeping up.
Request after request.
Exactly. Until, bang, the kernel steps in, the container gets killed, and the process restarts.
And the worst part is you can't find it just by reading the code. The code looks fine. The garbage collector should be working. This is the exact challenge Halodoc, serving millions, had to solve.
Yeah, it is.
So our mission today is to walk you through their systematic production-grade strategy, and we're going to focus on the one tool that gives you superpowers here, the Heap snapshot.
Yeah, and if you've ever spent days, staring at a graph trying to figure out what line of code is doing this, and, that just looking at the code is useless.
Right.
You can't see what's growing. You just know memory is going up.
Yeah.
The Heap snapshot gives you X-ray vision. It really moves the whole process from guesswork to data-driven forensics.
Okay, let's unpack this superpower then. Before we start capturing anything, we need to know what we're looking at. So, section 1. What exactly is a heap snapshot, and what's the one metric that really matters?
So a heap snapshot it's basically a complete frozen picture of your entire JavaScript memory heap at one specific moment.
Everything.
Everything. Every object, every variable, all the closures, it's all in there with all the connections showing how they relate to each other.
Okay, so you open one of these files and you're immediately hit with these two different size metrics. I feel like this is a trap. What's the difference between shallow size and retained size?
It's a huge trap, and this distinction it's absolutely crucial. So shallow size is the memory that the object itself takes up.
Okay.
Think of an empty array. Shallow size is just the memory needed for that array structure, not for anything you put inside it.
So it's just the container, which I can see how that would be misleading. A small container could hold something huge.
Yeah.
I've definitely been fooled by that before.
We all have. But the metric that really finds the leak is the retained size.
Yeah, that is.
Retained size is the total amount of memory that would be freed if that one object were garbage collected. It's the object's own shallow size plus the size of everything else that is only reachable through it.
Oh, okay, wait. Let me make sure I'm tracking this. So if I'm hunting a leak, I need to pretty much ignore shallow size and just laser focus on retained size.
Absolutely. 100%. You could have a tiny little object, a single reference, held by some global variable, right? Tiny shallow size. But if that one little reference is the only thing keeping a massive, 100 megabyte array of user data alive,
Yeah.
its retained size will be huge. That massive retained size is the smoking gun. It confirms you've found your culprit.
So we're looking for the delta, the change in retained size
Yeah.
between two snapshots.
That's it. That's the whole game right there.
Okay, that completely reframes the task, so we know what to look for. But how do you get this data in production? How did Halodoc handle capturing this on their massive SSR instances?
Well, the sources lay out 3 methods, sort of going from easy local testing to full-blown production integration.
Okay.
The simplest, of course, is just local development. You use the Node.js inspector, you run node inspect, open up chrome.inspect, and use the DevTools memory cab. That's for when you can replicate it on your machine.
And then there's the old school way, right? The external heap dump module.
Yes, which is the method that high-scale teams basically abandon pretty quickly.
Why is that?
2 reasons. With heap dump, you trigger a write to the server's local disk. So first, trying to drop a 2 gigabyte file off a server at 3 in the morning is not fun.
Yeah.
And second, and this is more critical, running a multi-gigabyte file to a container's tiny, often ephemeral disk can just fill it up and crash the container for a whole different reason.
So the tool to find the crash actually causes a crash.
Exactly. So you need something lightweight, something built in. And that brings us to method 3, which is what they adopted.
The gold standard.
Correct. They use the built-in Node.js V8 API. Since Node version 12, you have access to the native V8 module. You just import a write heap snapshot from node.v8.
No external dependencies.
None. It's fast, it's always there, and the file name it makes is really descriptive by default. It includes a date, time, process ID. Everything you need for traceability is baked right in.
That's the tool. Okay, now for the really impressive part. Halodoc's production snapshot strategy. How did they make sure they were capturing snapshots at the exact right moments?
They set up two critical triggers. The first one is, I'd say, mandatory. It's the baseline,
Clean
the
state.
clean state. This snapshot is taken the second the app initializes, but before it starts listening for any requests. That's your reference point for everything that follows.
And the second trigger is for that on-demand scenario. The metrics are spiking, an engineer is on call, and they need data now without having to SSH into a server.
For that, they configured their app to listen for the SIGSR2 signal.
SIGSR2.
It's a user-defined signal. It's generally safe. The OS doesn't really use it, which makes it perfect for custom operations like this. You can just tell your process, hey, when you get SIGSR2, run the V8 snapshot function.
But how does an engineer securely send that signal to a remote container? I mean, you don't want to give everyone shell access.
And this is where the security automation is so clever. They build a minimal private automation service.
Okay.
This service has one job and one job only. It's given what's called least privilege, RBAC role-based access control. Its only permission is to send the SIGSR2 signal to a specific container ID.
So it's a secure, auditable little button that an authorized person can press.
Precisely. No direct server access needed.
That's brilliant. Now, what about the worst-case scenario? The out-of-memory crash, the OM event? Did they have a plan for that?
They did. They set a specific node start flag,
Yeah.
heap snapshot near heap limit, and they set its value to 2.
2. Why 2?
This tells the V8 engine to try to capture 2 snapshots right before the process hits its memory limit and dies. It gives you some final forensic data without trying to write, 10 huge files on a system that's already unstable.
And I imagine the keyword there is try. The source mentions these OM snapshots aren't guaranteed, right?
Exactly. The process is just too volatile at that point. It might die before the write finishes. That's why the manual SIGSR2 trigger is so important. You want to capture the data proactively when memory hits maybe 70% before the system is in a death spiral.
Okay, now for the logistics. Storage and security. These snapshots can be huge, gigabytes even, and they're sensitive. So where do they go?
You can't leave them on the server's disk for all the reasons we just discussed.
Right.
The solution was to integrate storage directly. They mount an Amazon S3 bucket as a volume right onto the Node.js instance. So the snapshot file gets written straight to S3, completely bypassing the local disk.
That's a level of security most people don't think about for, say, log files. Why is a heap snapshot so much more dangerous?
Because it is literally everything in your application's memory.
Wow.
It's a complete dump. If you're handling user requests, that snapshot has active auth tokens, user sessions, maybe temporary PII,
Right.
encryption keys,
All your application secret.
everything. It is probably the single most sensitive data artifact your system can possibly generate.
Which means you need security protocols way beyond what you'd use for a typical log file.
Oh, absolutely. The S3 bucket has to be configured with server-side encryption, SSE-S3.
Yeah.
All public access has to be blocked. And they use a strict IAM policy, so only authorized audited personnel can even read the files.
I see. They also made sure there was no cross-region replication.
Yes, to maintain data residency rules.
Yeah.
And to control costs, because these are huge files, they just put a simple 15-day expiry policy on the S3 directory.
So they clean themselves up.
They delete themselves automatically. And there's one critical warning here. Taking a snapshot pauses the Node.js event loop.
It freezes the app.
Momentarily, yes, and it spikes the CPU. You should never, ever trigger these during peak traffic. Always schedule them for low traffic hours.
Very wise advice. Okay, so we have our snapshots, we have a clean baseline, and we have one from after the memory grew, section 4, the analysis. We load both into Chrome DevTools. What is the very first thing we do?
You immediately go to the comparison view. You tell it to compare snapshot 2, the leaky one, against snapshot 1, the baseline.
And what does that show you?
It immediately highlights the deltas. It shows you what objects were created and not destroyed. You'll see candidates with a big hashtag delta or, more temptingly, a big size delta.
So if I see something like plus string size delta plus 55.7 millibit, my brain just screams, aha, I found it, too many strings.
And that is the trap. It really is. Remember, size delta is based on shallow size.
Right.
That number just tells you a lot of new strings were created. It doesn't prove they're being retained forever. It could just be from a burst of normal activity. It's a hint. And a big hint, but it's not the proof.
So how do we get the proof? How do we confirm that this object is really the phantom holding our memory hostage?
This is the critical next step.
Yeah.
You switch from the comparison view back to the summary view, where you're looking at your larger second snapshot.
Okay.
You find that same object type, say string, and you immediately sort the columns by retain size, not shallow size.
Ah, the moment of truth.
That's it. If that collection of objects, which maybe looked only kind of big in the shallow size column, suddenly jumps to the very top of the list, showing hundreds of megabytes of retained size, you have your confirmation.
You found the leak.
You found it. The garbage collector wants to free that memory, but something is holding on.
And the final piece of the puzzle is tracing it back to the actual line of code.
You click on that leaky object, and you open the retainers pane down below. This shows you the exact chain of references, the whole graph, all the way back to the root object that's preventing it from being collected.
And that chain usually points to something like a closure or a global variable.
Often, yes. A closure that accidentally captured a big variable from its outer scope, a global cache that never gets cleared, something like that.
The docs we looked at had a perfect example of this with server-side rendering. A global cache array was storing a reference to every single incoming request object.
That is the classic SSR failure mode. The request ends, but the req object, with all its headers and data, it lives forever because that global array is still pointing to it. The snapshot proves the leak, and the retainers pane will point you right at that global cache.
And the fix is just clear the cache.
Clear the cache, or better yet, scope it properly so it gets destroyed when the request is done.
This brings us to a quick checklist for everyone listening. Section 5, common leak patterns to look for based on what Halodoc found. First up, lingering timers.
Yeah, if you see growing timer objects in your snapshots, it means you're not cleaning up. The fix is simple. Always call clear interval or clear timeout when a component or a request is torn down.
Next, something very specific to environments like Angular Universal, unclosed RxJS subscriptions.
Right. These show up as growing subscriber or subject objects that persist across requests. You have to explicitly close these streams. The fix is using RxJS operators, like take until destroyed or first, to make sure the stream completes.
Improper dependency injection seems to be another big one.
Absolutely. If you have a root-level service, one that lives for the entire application lifetime, and it's holding on to growing data, that's a problem. You need to scope that service more narrowly so it gets torn down with the feature or component that uses it.
And finally, back to those tricky closures.
Closures are just sneaky. They'll accidentally hold on to the entire rec or res object. The fix is to be explicit. If you need something from that object inside a long-lived closure, just copy the one field you need, like a user ID, or explicitly set the reference to null when you're done with it to break the chain.
So this whole process, identify the rising memory, capture your snapshots, compare them, trace the retainers, fix it, and verify. This is how you move from guessing to data-driven stability.
It's how you stop waiting for the crash and start proactively hunting for the cause. It ensures performance and stability, especially for these services that just can't afford to go down.
As we close out, I want to circle back to the security measures Halodoc put in place. The server-side encryption, the strict IAM policies. Why treat this debugging tool with the kind of paranoia you normally reserve for a production database?
Because, again, a heap snapshot isn't like a log file. It's the complete runtime state.
Yeah.
It has active session tokens in it. It has environment variables. It has real user PII that's in flight.
So here's the final provocative thought for you. If you start using heap snapshots in your debugging workflow, your very first priority has to be treating those files like an unencrypted, real-time backup of your system's most sensitive data.
Absolutely. They need immediate, automated encryption and highly restricted access the second they are created. If your storage plan isn't already set up with policies like SSES3 and strict RBAC before you write your first snapshot, you need to stop and fix that first.
Because performance stability and data security are, in this case, the exact same problem.
They are inextricably linked.
A deep dive into the intersection of stability and security. Thank you for walking us through the Halodoc strategy.